In this video, we're going to look at the curvature of a straight line. So let's say this straight line here is given by this position vector. So this is your constant vector. So you can imagine the C as being 1 across and then 3 up. 1 across and then 3 up. So this is your constant here. And then this is your vector here. So 2 across and then 1 up. 2 across and then 1 up. So a second later, it would do another 1 across, 2 up, and then another increment of time would be 2 across and then 1 up, and so on. This thing here describes this straight line. So to work out the curvature of this straight line, we've seen this formula before. First, we need to work out the tangent. So when given the position vector, if you differentiate it, it will give you your tangent. It will give you your, imagine as being like this, it will give you your tangent, but we want the unit tangent of magnitude 1. So anyway, starting from here, differentiate it, that will then give you your vector here. So in our case, it would be 2, 1. So in our case, our vector here would be 2, 1. So that would then give us our vector, but we want a unit vector. Remember, we always have to work with unit vector. So we got to work out the magnitude. Work out the magnitude of this. So differentiating this will then give us this thing here. So now we want the unit tangent. So get the magnitude, which is 2, 1, 2, 1, divided by the magnitude. So the magnitude of this would be 2, using Pythagoras, which is root 5. 2 squared is 4 plus 1, 5 root it. Well, the magnitude is root 5. So this unit tangent would be given by this thing here. So let's start again. We started out with this. Differentiate it. That will then give you your tangent. But then we want a unit tangent. So work out the magnitude and then divide this vector by its magnitude. That will then give us our unit tangent. So that will then give us our tangent of magnitude 1, our unit tangent. Now that we've got our unit tangent, we need to differentiate it with respect to t. So now that we've got our unit tangent, we need to differentiate it with respect to t. You see, when you differentiate this, it will give you 0. Because here, if you look at this, you've got a t here. So when you differentiate this, it will be 2, 1. It will be 2, 2, 1 as a vector. Here, there is no t. So when you differentiate this, it will be 0. So looking at this here, this thing here would be 0. The magnitude of 0 is 0. So this whole thing here will be 0. 0 times this thing here, it will be 0. So the curvature kappa is equal to 0. So the curvature of this straight line is 0 as you expected. So let's try and understand what's going on here. Hang on. So let's look at this from a different perspective. So you've got your straight line here. This describes a straight line like this. Remember, curvature is defined as the change in the unit tangent with respect to arc length. So let's just imagine the particle is traveling at a constant velocity. So we would split this up into equal ds's. So split all these up into equal ds's. So 1 second, the particle travels from here to here, and then another second, it will travel from here to here. So when you look at kappa is equal to change in the unit's tangent vector over change in the arc length. So if you look at this vector here, this vector looks like this. I'm enlarging it, and then this vector here would be exactly the same. So dt would be 0. dt would be 0 divided by whatever length this may be. I don't care, but it's going to be 0. So let's imagine the same scenario, but the particle is accelerating. So it's traveling faster and faster. So in 1 second, let's say it's here, and then in the next one, it will be a lot longer. It will be a lot longer. Let's just imagine it to be somewhere around here. So remember, the particle is traveling in a straight line, but it's accelerating. So this magnitude would be different from this magnitude. So hang on. So the first magnitude would be this. The second one would be longer. It would be this. So dt here is actually this bit here. There is a change in dt. there is a change in dt. But the thing is, now you've got to differentiate it with respect to arc length. Arc length is in the same direction. It's like me giving you this. Don't forget, this dt here is this bit here. And then I'm asking you to differentiate it along the same path, So it's like me giving you this, x, y, and then it's like me. So you can imagine dx is in as the change in the x direction. It's like me asking you to differentiate this. It's a horizontal line. So in this case, dy by dx is 0. Let's say if I give you this, y equals 4. If you try and differentiate dy by dx, it's going to be equal to 0 because it's traveling. That dx is in the same direction. Dx is in the same direction. This is in the same direction as dx. So going back to here, yes, there is a. Let's start again here. So the particle is like this. So the first magnitude is this small one here. The second one is a longer magnitude. So this dt here is this bit here. But then you're differentiating it with something that's parallel to this. So if I were to give you this, let's say, and then ask you to differentiate it, so even if you're not on the line, you're parallel to the line, it's still going to be 0. So the point is that this thing here, dt here, is parallel to the arc length. So when you differentiate it, it's going to give you 0. It's just like me asking you to differentiate y equals 7 with respect to x. Well, they're parallel, so the gradient is going to be 0. So I hope you can accept that because this is parallel to ds, then when you differentiate it, it's going to be 0. Okay.